All right. Hello and welcome, functions class. Friday afternoon, spring break. I'm recording a lecture on finding the line of best fit for a bunch of data by hand. So please take out this packet, which I passed out on Friday, called Introduction to Linear Regression. And on this packet, you will find a, let's get a new marker. On this packet, you will find a couple of data points. And the data points are 619, 1120, 1625, 1925. Please take a moment and plot them on your graph. And when you do so, you should see something that looks pretty much like what I have here. It should look better on your paper because you have an actual accurate graph. All right, goal. Oh, and by the way, what we were doing is we are shifting basically from chapter 7 to chapter 8. In chapter 7, we were looking at patterns in data, but all the data was fake. And so there was always a function which went exactly through the data. But in the real world, or in the real fake world, as I like to call it, or the fake real world, there's a difference. In the fake real world, the data is not going to fit a function exactly because you're taking measurements or it's some kind of science or something like that. And so we would still like to figure out the function which best goes through that data. So that's what we're doing here. All right, so we're going to start today with just linear data. And we're going to take these 4 points. We look at these 4 points and we see that, roughly speaking, these 4 points form a line. Now, not exactly a line, but roughly a line. There are certain ways of measuring whether it is appropriate to use a linear model to fit that data, but we're not really going to talk about that either right now. And in reality, with only 4 points, it's kind of a joke. You should have, hundreds of points or something like that, and then you can actually sort of talk about model fitting. All right, how do you find the line of best fit for a bunch of data? Well, first we'll talk about the 7th grade way. The 7th grade way is you take a ruler and you pretty much just stick the ruler in a certain place where it kind of looks like, yeah, that's pretty good. And once you think that's pretty good, then you draw a line, and then you look at the y-intercept of that line, and it's like 14 something, and then you kind of like count boxes and you figure out the slope of the line, and there's your line. Actually, this method is not so bad at all, and does produce a kind of a line of best fit. So I want to encourage you to realize that there's not just one line of best fit. There are many different ways to come up with a quote-unquote line of best fit. And one way is just to kind of look at it and just draw a line that seems to mostly go through the points as best as you can. And then the advantage of that line is that once you've drawn the line, then you can predict if this is some kind of scientific relationship, like number of inches above. Well, I don't know. I don't even know what this could possibly be. Number of minutes spent studying for speed trick quiz versus number of attempts it takes to, I don't know, something dumb like that. Then you could use this. You could use these other numbers to plug into the line to get the line of best fit. All right. I would like to talk about a more mathematical way to calculate the line of best fit, so let's do that. So what we have here is a proposed line, and we call this y hat. So and this proposed line is 0.6x plus 14. What this is a it is a model for this data. How good of a model it is, we're going to find out. Okay, so please draw the line y equals 0.6x plus 14. I will try to draw it here. Let's see, how do I do this? 3/5, so up 3 over 5. Over 5 again. I should be at 20 by now. Over 5, up 3, I'll be at 23. Something like this-ish. Okay, so I seem to have a line which looks Oh, this actually looks pretty terrible because I can't, because my stuff is bad. But anyway, let's suppose that that is my line, something like that. Okay, well, notice that this particular line is not so bad at all. It's actually pretty decent, and I'm pretty happy with it. How good is this line? Well, what we want to measure is by how much it's off. How much is it off by? Well, the only data that we have are these particular points. So if I want to measure how much it's off by, I have to use the points. And what I do is I calculate what are these things called residuals. And the residuals represent the distance between the actual point and the expected point. So we define a residual. Residual is y minus y hat. A residual for a particular x value is the difference in the actual y value minus the y value predicted by your linear model. Okay, and essentially with these residuals we want them to be as small as possible. If the residuals are very small, then it means the line of best fit is a good line. If the residuals are very big, it means that it's a bad line. Okay, well, one very naive thought that you might have is why don't we just try to make the sum of the residuals as small as possible? That seems like a good idea, but the residuals are sometimes positive and sometimes negative. So if all we wanted was to figure out when the residuals are as small as possible, we would end up with these kind of ridiculous examples where, okay, suppose I had a line, let's see if I can do this. Suppose I had data that looked like this, that was almost exactly on the line. And now here is my proposed line of best fit. Intuitively, we feel that this line of best fit is pretty terrible. Here, because the residuals are big, but since we define the residual as y minus y hat, then these residuals are all going to be negative, and these residuals are all going to be positive, kind of canceling them out. Okay, so it can't be as simple as just saying, where are the residuals as small as possible? Alright, so second idea, hopefully you all get this. Second idea is, let's do it so that the absolute value of the residuals is as small as possible. And that is a actually completely legitimate and viable idea, but that's not what we're going to do. And we basically don't do that for more or less silly historical reasons, but basically the algebra works out better if we just use squares instead of absolute values, which also makes it positive, so that also works. Okay, so here's a chart. Follow this chart with me. Not sure how well this lecture actually works without people being here. So we have this chart, and what I'd like you to do for each of the x values and each of the y values, please compute the expected y value. Okay, so if x is 6, I have to do a bunch of math in my head now. If x is 6 and this is my linear model, then this would predict like 17.6, I think. That is right, right? 3.6, 7.6, yeah. 11, that's going to be 6.6, 20.6. 16 is 9.6, so that's 23.6. 19, 60, and 54 is 11.4, so that's 25.4. Okay. So, this is basically saying that the model predicts, just as my picture more or less says, that is 17.6, so the predicted number is a little bit less. This is 20.6, so that's called bad graph. And this is 23.6, which also doesn't look very good, but that number is 25.4. Okay, cool. So now what I'll do is I'll calculate the residuals for each one of these points. Calculate the residuals. Residual is y minus y hat, so we just do it. It's 2.6. No. 1.4. Yeah. Negative 6. 4. Negative 0.4. Oh, this is right. Patrick, check my work. And then we square the residuals. So we square each of these numbers. That's 1.96, it's 0.36, it's another 1.96, and it's 0.16. We add these all up. That's like something, 18, 19, 24. 4.44. So I think that for this problem, the sum of the squares of the residuals, sum of squares of residuals equals 4.44. All right, and this is the metric which I am going to use to determine whether a line is a good line or not. Based on, I'm looking for the line which minimizes the sum of the squares of the residuals. Is this good? I don't know, let's find out. Turn to the next page, and on the next page, same data. Now we have a different linear model. Please do this computation again. For each of these points, predict the y value, find the residual, take the sum of the squares of the residuals. And I guess I'll do it too. I think I'm just going to cheat and use a calculator. All right. 18.3, 5. 5.45. Is that right? Sure. Okay, so this is 0.7. Okay, now these numbers need to be squared. 9. No. 105, 1.05 squared. Man, that's hard. 5 times 105.
It's 5 times 105.
10,000.
Just 5 times 105.
Yeah, that's 1.1025. That's 1.44. Yeah. And 0.45 squared is 0.2025. So if we add these all up, we get, I don't think this is right. Anyway, I don't care. What we get is 3.235. I have no idea if that's actually right or not. Oh, is all this happening off camera? That's kind of sucks. So I think, anyway, this is more fun when you guys are here because then I don't actually bother doing it. I just kind of like wander around the room and wait till someone finishes and then just shout out, hey, did everyone get that answer? And if so, it's good. But I think the moral of the story is you get a smaller number. This is smaller. And since the sum, and that might even be the right number, then what happens is, what we see here for this line then is that the sum of the squares of the residuals is less than the previous one, and thus we judge that line to be better. Okay, this method, this is not even a method, this crap which I'm giving you is obviously totally insufficient. I'm just giving you a bunch of models and we're testing how good they are. What I want is a method which will come up with the best model. And this is what I'm going to show you in a second. How do we do this? Well, here is the idea. We take some data. So, by the way, we call this line the least squares regression line. And I will not attempt to explain the word regression in functions. You'll learn about that in statistics. So let's take, for our purposes, some very, very simple linear data. 3, 5, 7, 1, 6, 8. And what I'm going to do with this data is, what I want to do is I want to find the line of best fit. In other words, find the line such the sum of the squares of the residuals is as small as possible. In other words, if we call y hat mx plus b, then find the m and the b such that the sum of the squares of the residuals is minimized. Okay, I'm going to pause for a second, and then we're going to do this on page 3, and then we'll be done.